Hello, how are you? Today is Saturday, December 14th, 2024, and today I am going to be talking about video understanding models. If you like this video, please like, subscribe, and follow if you get a chance, and I would appreciate it much. It helps me go through and try to make more of the videos and give you more of what you want. Okay, so today we're going to be talking about video understanding models, part 1. This is a larger topic, so we're probably going to cover some of the higher level stuff, but in order to get into some of the more specific stuff, I will have to make a much longer video, and I'll talk about what that means in a bit. So I'm going to be talking about starting with the basics, then I'm going to be going into the models themselves, then I'm going to be talking about the kinetics dataset, which is an action recognition dataset made by DeepMind. Then I'm going to be talking about models, and then I'm going to be talking about evaluation of those models a tiny bit. I'm not going to go too much into that aspect of video understanding models just yet. So let's start with, before we get to video understanding, we have to do a recall on what image understanding is, right? And so image understanding forms the basis of computer vision. Okay, all computer vision requires some sort of system, whether it be a model or some sort of heuristic system to understand the content of images. It involves recognizing objects, scenes, and patterns in static images. So as you can see on the right, you have a cat. You have a cat with a bounding box around it, which is the task called classification and localization. You have an image to the right of that with 3 bounding boxes around each actor in the image, which is object detection, and you see it can detect cats, dogs, ducks. And finally, you have this other image to the right of that, which is an image of a smooth manifold around the creatures, which kind of like outline is very specifically. It's not a box, the regions that the creatures exist in. And so those are cat, dog, and duck. Again, so image understanding, once you can do image understanding, you could do more advanced video understanding tasks. And these are just some examples, but more examples include object detection, face recognition, and scene categorization. So the basis for image detection are convolutional neural networks. Okay, convolutional neural networks are essential for image recognition tasks because they are designed to break down images effectively and into the features that best describe the image computationally in these so-called feature maps. The image of the network architecture is to the right, but progressive layers of the convolutional neural network break down the image into feature maps, which then finally get sent to a fully connected standard neural network, which can then actually classify what is in the image. And the image understanding is done via these convolutional layers because they are very effective at picking out patterns and different categories of resolution of the image data. And when I mean resolution as broken down by these convolutional filters. We're not going to go too deep into how CNNs work. There's plenty of videos on that and a lot of content on that out there. But generally speaking, they work by scanning the images with filters and recognizing patterns. So they can recognize characteristics of this 3 to the left. They can recognize other characteristics of other letters and whatnot that are specific to those letters, like the stems, the curves of the letters. All these kind of abstract characteristics can be broken down and understood by these models. And then CNNs are widely used for image classification and object detection, and pretty much all the tasks that you saw over here. Okay, so now you could use there's different variants of CNNs, and there's also other models, which like vision transformers, which also allow you to do some of this stuff. But essentially, the task overall is the same. Now, what happens with image to video? Video adds a temporal dimension beyond static images. Video is not just one image, it's a sequence of images. And why that's important is because each image on its own has some context and something can be inferred about that image from the presence of who's in that image and what's happening in that image. But emergently speaking, the video itself through a sequence of several images tells you what is actually happening. For example, the image of this couple on the right, if you had only one shot of them, you wouldn't necessarily be able to tell that they're dancing. They could look like they're just holding hands. I mean, maybe you could guess that this is a dance studio and it says swing dance to the left, but let's say that wasn't there. Then the only way you'd really know that they are dancing is that you'd have to observe the actions they're taking throughout a time period of their presence in that area. So at this point, it just looks like they're simply standing there, but the video would tell you that they're dancing. Now, in order to determine what's happening in a video, there's many different kinds of video understanding. And many of those types involve motion tracking. Okay, so motion tracking is one of the, I guess it's complicated, but it's still, a lot, it's one of the easier tasks overall because full context is not required to be understood, but maybe the location of objects. But in addition to the location of objects, or because of where the location of objects is inferred from, something about the context of what's happening in the video can be determined. Models must now track sequences of frames and not just one image, as I said. And the sequences are important, and if sequences are left out, sequences can also change during the course of the video. So if sequences are left out too, then the video understanding model would have to account for gaps in understanding or changes of scenes from one scene of dancing, say it moves to playing football, say it moves to playing hockey, say it moves to playing dancing. Those sequences or segments of activity have to be understood sort of separately. And spatial temporal analysis is important for video analysis. Information is important for video analysis, and so spatial temporal information is not temporal. The spatial part is the RGB frames of the image, and the temporal part is the time dimension, or what's happening, how the images are changing over time. And we have to define how we track the how in the way images are changing over time, because that in itself is a little bit of an abstract concept if you try to separate that from the change of what's happening from frame to frame. So what are some challenges in video understanding? So one of the major challenges that are even before the model selection is done is that the fact is that video data is large scale data, right? And has high computational costs. And these are like the main things. Like there's a lot that goes into video, right? There's a lot that goes into storing video. There's a lot that goes into pre-processing video and distributing video and compressing video and making different resolutions of video available. So it's in itself, there's a lot that happens just because of the fact that we're dealing with video. Now, another thing that's challenging with videos is that there's this principle of temporal consistency across frames, right? So temporal consistency means like, in videos where like not much is happening, or very little activity is actually happening throughout the video, there's a high temporal consistency from frame to frame, because with every frame in the video or in a segment of the video, remember, also note that temporal consistency can exist as a concept in segments, right? As in higher in some segments versus other segments. But temporal consistency of frames is difficult because in many scenarios you don't have like a smooth, single, simple activity happening through a video. What you'll have is many different activities occurring throughout the course of the video with potentially many different camera angles shot of the video observing these activities. The model becomes more challenging in that case for the model to understand what's happening. Real-time processing is a significant hurdle in video analysis because real-time processing of image requires specific models. Like for example, the YOLO model is good at real-time processing of images while sacrificing some accuracy, which is in contrast to a network or a model like RCNN or something like Detectron. And the reason for that is because, again, you're doing a different type of classification. But in videos, it's even more challenging because videos is the repeated application of that model. And not only in itself, but combined with other processes to determine what's happening. So if you need to do this real fast in real time, then you have to get fast, accurate detection, which is a challenge. Models need to handle variations in lighting, movement, and context. And again, this makes it difficult because what if the video content itself is not easy to distinguish, right? Like, for example, if something's happening in a kind of dimly lit area and the area increases in brightness, so you could kind of see a lot of motion and then it becomes dimly lit again. It's not easy to tell exactly what's going on. It's not maybe in some cases even easy for a person to tell what's going on, but much more so a person than a machine that doesn't have the training to understand a lot of what's happening. Yeah, in this case, there's a lot that can happen that will cause what's called cycle consistency loss. And basically, this is a feature of the embedding space where embeddings essentially diverge between videos, even though the video context was initially similar, and the divergence becomes problematic for the model to handle because, again, a lot of the principle of understanding what's happening for a neural network occurs with matching in the embedding space via some function, matching function, similarity function. And so if the similarity becomes large, even though the videos started off similarly, then you would have an issue with resolving where this action should be classified. Okay. So we're going to talk a little bit about traditional methods of tracking. One of those is called the mean shift tracking. And I'm not going to spend a ton of time on this because essentially there's a lot that can go into this study, and there's a lot that these algorithms can still be used for. But essentially, mean shift tracking relies on finding the statistical mode of an object's feature distribution. What does that mean? So given that an object is kind of maybe moving through space in some way, right? If there's features associated with an object, an example would be color histogram. So you could imagine the color histogram of an object shifting in particular ways as the video progresses. We can understand maybe where the object is going, okay? And so what we're looking for is like the average overall shift of an object to tell its kind of motion through observing its features rather than things necessarily like its position. And what happens is there's a window that's shifted iteratively as the mean of the feature space of the calculated features in this feature space shifts along with it, and it sort of shifts and where it moves to is towards a location of higher probability of the target's appearance. And this operates frame by frame, updating the position of the tracking window as the object moves. So as we're moving through space, the object's moving, and then the window itself is changing to accommodate this. And then it sounds simple, but it's a simple way of like detecting certain changes in the video. But the problem is, again, this works for simple contexts. If your video is complicated and you're tracking more than one object, then it's a little bit harder. The color histogram might not be moving in a clear way, or the histogram of the object might itself be distorted by the presence of another object. And then performing mean shift tracking on that becomes impossible without specialized knowledge of what's going on in that histogram. So then we're going to go, before we get to the deep learning stuff, we're going to talk about traditional methods. And one of those is called visual bag of words. What is the visual bag of words? The visual bag of words, and you can think of visual bag of words like the bag of words model when it comes to NLP tasks. But the visual bag of words is an older technique which represents a content as a collection of discrete code words, similar to how text is represented by words in a document. So essentially, we have a process of we take images and then we break those images down into segments that logically separated segments, which I'll get into segment separation 10 times fast. Segment separation part pretty soon, but essentially that's what happens. So this bag of words, or this segmented separation of pieces of an object or a scene, forms what's called a vocabulary. by clustering all the image descriptors and then converts the frames of these into histograms of these visual words, right? So, for example, so there could be a particular document, quote unquote, that contains certain number of these features from these bags of words, and there's a frequency counter here, which kind of detects like how much, and that frequency counter is represented by the histogram, but it detects how many words are words, quote unquote, or image features are represented in a particular image. And so, for example, like if you have more mouths visible, then you'll see the more count of mouths increase, or whatnot, or more spokes on a bike, you'll see the number of spokes increase. Anyway. So it transforms complex imagery into manageable frequency vectors. And that's what it is, because imagery is complex. That's why we need a more complex network, like a convolutional neural network, to understand the imagery, which does hierarchical feature extraction. So in this case, when we have this visual bag of words, we can treat each of these sub-images and the end result as a frequency vector. Right, and this is approaching what we would do like in embedding space, except this is working directly on features. And this is a straightforward method for characterizing scenes, but it doesn't talk anything about temporal order. But you can imagine this being somewhat present in a video understanding model that's trying to understand what's happening in a video. And then finally, we have this concept of the hidden Markov model. The hidden Markov model treats frames as sequences of observations targeted by underlying hidden states, objects, positions, or actions. So what this model here reminds me more of is the way that people do predictions on a system. For example, and also I have this a key here for this prediction of your mood based on the weather. And so there's a transition probability between states that says that, if you're for example, you start off with the state sunny and the state rainy, and there's some percent probability that the start of the day will be rainy with a small percent and sunny with rainy with a much higher percent, sunny with a much smaller percent. And if it's sunny, what will happen is that it will be happy with about 80%, but only grounded with 20%. And the reverse is almost true for the rain node. So ultimately your chances of transitioning to happy or grumpy. So it's essentially, it can be modeled as a coin flip. So the Markov models again have their uses. They learn probability distributions for transitions between states, hidden states. And they talk about how objects evolve over time and allow you to essentially do sort of prediction, quote unquote, on the state of the system. The inference techniques, such as the Viterbi algorithm, are used to determine the most likely state sequences given the observed data. And don't worry about the Viterbi algorithm. It's used in communication systems, but I guess in this case, they made an exception, or there's an exception to particularly facilitate the transition states in hidden Markov models. And this allows for overall this state transition probability is advanced from the previous methods because they do allow for temporal modeling. But the issue is when marrying it with the image modeling is more challenging. So the temporal modeling often requires careful feature extraction and may struggle with high dimensional or rapidly changing visual input. So again, this is something, the Markov model is pretty set once it's done, and it has to be rebuilt every time. This is why there is some amount of inflexibility here, even though this model actually does work in some certain contexts, but in context to the general task, we'll get to the better model soon. So how do you train video understanding models? We'll start with the kinetics data set. The kinetics datasets are large-scale video datasets created by DeepMind specifically designed for action recognition videos. So there's a bunch of these videos, and they have a single action occurring in each video, which, for example, if you look at these samples, there's actions for applying eye cream, for arranging flowers, for auctioning, for applauding. And this is one of the simpler datasets because the action recognitions themselves are pretty straightforward. But there could be more complex data sets. There are more complex requirements, which would require more complex data sets. So this includes kinetics 400, 500, and 700, which each iteration expanding the number of classes and videos. Kinetics 400 features 400 human action classes with over 300,000 clips, while Kinetics 700 includes 700 classes and 650,000 clips. So this is widely used in video understanding, this model. And there's like much research going on around this model. So that's what we want to do here. We want to do some kind of research on these models. And we want to like be able to do segmented action recognition. But let's get to a more advanced of data set. There's a data set called AVA Kinetics, Atomic Visual Actions. And what the Atomic Visual Actions data set is a list of Hollywood videos that has bounding boxes around each of the actors in the video as being associated with a particular action. Okay, and so again, these are videos of famous people. Why that 100% matters? Well, maybe it does, but for visibility purposes, and I don't know. But you know, at this point, that's what it is, and it provides actions for a fine temporal resolution in 1 second intervals using bounding boxes. Okay. Yeah. So that's what I just described. There's over 80 atomic action classes in this AVA Kinetics set, allowing the detailed action recognition across diverse scenarios. That's very robust. Turns out that's maybe not enough. I'm sure you could think of more than 80 actions that a person can do, but really this is in the commonplace case. It uses 15 million segments of Hollywood movies, offering diversity in interactions and environment compared to curated data sets like kinetics. So this is just kind of raw information flow that's coming from these 15 million clips, which is interesting because the labeling is, you know, less. It's present, but it's in a way interacting with the model differently. And the good thing, the important thing about this AVA Kinetics set is that it focuses on multi-person interactions and relationships in video frames, pushing models to infer context beyond isolated actions. And so basically, you can see this image on the right. There's something that's like occurring between both. One is trying to, it looks like, do the high jump and has lost and dropped the bar. And the other person is, I think, carrying a pad to determine how high the person got before falling with the bar. So there is definitely interaction occurring and a dependency between interactions, and that's what we would need to capture if we were doing something like, you know, scene understanding. Here's the paper. And finally, the most advanced version is the Charades dataset, which is overlapping in sequential actions annotated at the frame level. So it enables training on multitask action prediction. So there's what it does is has, you know, a great number of videos also on everyday tasks like cleaning or doing things in the home environment. You know, and you can see why something like this could be important because there could be, you know, robotics at home that require vision models to understand. And there's annotations required for longer activities because there's more to say about what's happening in those activities. And the other thing is it emphasizes joint modeling of objects using human action. This is important because in isolation, the previous actions, you could determine what they're doing in that single context, right? Like two people salsa dancing, right? Two people, maybe a person climbing a ladder. There's a single individual context. But like if you see like somebody climbing a ladder and then being thrown down a rope and helped up and then getting to safety and then eating food on top of a mountain, what happens is then it, like, you know, and then like working with somebody else to be pulled up, right? And then the other person gives them a drink, and then the first person takes the drink and they start to pat each other in the back and talk to each other. Whatever the case is, there's complex interaction happening between multiple actors where kinetics won't necessarily solve. So we need to have a much more robust training set like charades or the AVA Kinetics. So what are the computational costs of video understanding? I've gone over them a little, but processing sequence of frames, demanding in video data, requires a lot of computational power. Models need to, again, employ spatial and temporal reasoning, and they have to. There's going to be a lot more GPU/vector/matrix processing occurring. So essentially, the hardware is going to be much more significant than plain old image understanding or text understanding. The need for real-time performance in applications like surveillance and autonomous driving requires high computational efficiency. Real-time performance, and that's the key word there. If something requires real-time performance, then we have to get more and more complex models, and especially if real-time performance is not supposed to cut any corners, right? And then we have different models that cost different amounts depending on the training and have trade-offs in the cost domain. An example is fast and transformers attempt to balance performance and inefficiency, but still require significant resources. So again, it's not the most tenable functional use. So let's continue on to the fun stuff. We will talk about now what's called optical flow. Optical flow is the idea of taking a space, some kind of ball moving in space, and having an example of an image moving in space and creating sort of a flow gradient of the image moving through space. So let's say that you have this ball here, and there's this vector map. You can think of this like a wind map or something like that, where the ball is moving in a particular direction, but it's actually related to the motion of the pixels. Optical flow has been around for a long time, and it has been one of the ways that classical video detection has been able to do things like motion tracking. In some sense, this is related to mean shift tracking, which I described earlier. And again, it describes how pixel moves from one frame to the next. Optical flow is essential for action recognition. So if you need to know, like if you can isolate a particular action from the rest of the window or environment, right? Optical flow will give you the optical flow understanding allows the model to really pick out which category of action a person is taking based on its training, because the optical flow from the training data in the embedding space will match the optical flow, or should closely enough match the optical flow from the actual object that you're trying to observe. And this whole principle is combined with CNNs or used in two-stream networks to enhance motion analysis, right? So that's what we're going to talk about in a bit. But all right, let's talk about the two-stream network. So this is the first pure video understanding model, okay? Not just an image model, but video understanding. So what happens? What does this neural network do? So the neural network architecture, again, it's more involved in the determination of the end result, but there's a lot of things that are similar in terms of layers to how convolutional neural networks work. There's also a fusion stage, and I'll go over what the inputs are, the intermediate streams are, and then the final fusion stage. So what happens is the two-stream networks separate spatial and temporal information. The spatial stream processes appearance, RGB frames and single frames. So appearances in the RGB frames, those frames you see, like the still of some image or the still of me, is essentially an RGB frame. And so there's going to be that data in isolation that's separated from the temporal stream, which captures motion through optical flow. And the motion is its own, the optical flow. This is why I described what the optical flow was, because the motion itself in a video, in many cases, or in all cases really, is described by optical flow. Okay, now on its own, right, this can be very complicated, because you can imagine that while in the single actor case it might be straightforward to see where optical flow is going and understanding what's happening, because a person kicking a soccer ball is a very well-known process, right? And it should be easy in theory to train that entire sequence into a model. But then it can get more complicated when you have different objects moving around and their optical flow vectors get messed up, right? So it's something to consider, because models are good and then the models are bad, and they have alternating performance over the time. But the other thing is that two-stream networks are used everywhere in action recognition tasks. So you can't argue with success, I guess. There's the paper there. Then, more and more interesting model for me is known as the I3D, inflated convolutional neural network, right? And the inflated convolutional neural network inflates a 2D CNN into the spatiotemporal domain. What does that mean? Inflate the 2D CNN. If you have, if you understand how the spatiotemporal, how CNNs work, right? CNNs take in image data and convert them to features and classifies them. So the same thing can happen here, except you would be inputting a time and audio stream together, and a time and image sequence stream together, and how you would actually model those together is the question, right? But the network captures both motion and appearance simultaneously. So, for example, as an object is changing from frame to frame, convolutions are done on the object and they're compared over time along with optical flow to determine, well, is this optical flow quantity itself represented somewhere in your vector store, for instance, or your embedded storage or not? And I3D models have been successful in action detection. Okay, and this is, again, you would assume if I got to this point that they were already active and they're already successful, maybe. And they're used on large data sets like kinetics for performance evaluation. So you'll see, I'll get a snapshot of the leaderboard to you a little later. And here's the demo I've made of the I3D CNN. I'll skip to the parts that are about video understanding that are interesting.
Describes it objects, an image, but what's happening within an image. An image, we can also pre-train this model, put in a particular locally image. So I'd like to note happening within a video.
Okay, so here.
I'd like to note action is occurring in the text. I upload an image.
So I built this tool, which you can upload an image to a service, which I have running in the background. That actually does the inference, right? Once the pre-trained model is installed and built, and that model is the inflated 3D convolutional neural net here. And so what happens is, as the video progresses, you see a series of probabilities associated with what's happening on the video and a particular action. As you can see, the soccer ball has a certain action with it, and there's other smaller actions there, but the most prominent one, and there's also goal, but the most prominent one is the soccer ball. And I didn't finish that one, but I'll just show you the rest of the video.
In the video. It's person's playing soccer, and then there's a probability of what action is occurring. One thing I would like to note is that the model is actually pretty powerful. I can build this example, I don't have it in it, but if there's multiple things happening within a video, the model can actually do segmentation. And so you can see the model can get as granular as knowing exactly what type of stroke it thinks this person is using, a breaststroke, butterfly stroke, and there's lower probabilities of other actions, but it can detect this person is swimming. Essentially, if multiple things were happening in the video, the model could be built to output separate probabilities per segment, so you can see several things happening simultaneously. And here's another example of a person, two people performing an action, and the model clearly knows that this action is tennis, and it persists to be tennis throughout the good deal of the video. So, and that's video recognition models using inflated convolutional neural nets trained on the Kinetics 500 data set. Very powerful tool, which we can do a lot with potentially. And let's finally look.
Okay, so that's basically the I3D CNN demo. Okay. So I'm not going to show you the architecture for that network, but it's similar to the convolutional neural network in that the convolutional neural network now is taking both the time sequence of data, which can be represented as a matrix, because we talked about optical flow being representative of what's happening over time, and also the frames themselves in isolation to do image detection and image understanding, which is required under the hood as well.
Okay, I have.
So basically, this is what I call this. I have this uh, additional demo that I've done that what it does, it attempts to break down what's happening in the video frame by frame using spatio-temporal information and a model called faster RCNN. So this is more about like object presence in a video and can be used in combination with a video understanding model to get perhaps even more nuanced context in a video, or output even more nuanced context from a video. Region CNN, we're not going to go too much into it. Just know that it's an advanced version of the convolutional neural network that allows for region detection and understanding what's happening in regions, thereby understanding object region segmentation. So faster RCNN excels in detecting and localizing objects in individual visual frames with high accuracy, and treats each frame as an independent enabling frame level object. So that's the way that you can model over time the presence of what's happening with particular objects. And then if you combine this objects with temporal processing, you can do more types of action recognition. What I'm going to show you here is actually pretty straightforward, but you could get pretty advanced with this. So so basically what I did, I uploaded a video. And I'm in Colab, by the way, and
Okay,
I have
so
my
the
code
video
running
has been uploaded, and what we're going to do now is we're going to play the video, and as the video is playing, the predictions are going to come through for each frame.
And so we're loading the video, and there we go. We have the video.
As I run this,
You can see that there's some detection
you can see
probability.
the frame-by-frame output
in each frame
is being loaded.
It thinks there's a lot of
and
potted plants there.
For the most part, so you see frame 1, frame 2.
And so there's going to be a consistency of what's happening.
And so these frames are not like individual, these are just sections of video. And so you'll see that there's going to be a lot of output per frame. The percentage will change, but the scene is not really changing very much. So what we can do, so you'll see a pretty much consistent probability here, but sometimes it'll vary. It'll pick out things like, oh, since there's foliage, then there's a percentage of a potted plant. And sometimes it picks out dual categories of what's present in the video. But I can go, and Common Cocos is actually, it's somewhat robust, but it only has like 96 labels. We can create a more robust data set if we have more labels associated. So as you can see, all sections of the video in terms of frames had output here.
Okay, now let me just give you a quick example of what I've done with video segmentation in another video in general. And this is kind of a segue from video understanding, but if you think about it, this can feed into video understanding, and let me demonstrate. So let's say I have this video of like driving through a city, right? This is just some random video of driving through a city that I found, right? It's moving pretty fast because I have the sped up version here. But let's see, we can do a few tasks with it. So let's say we can do background removal. And as you can see, this video on the lower left has the background removed from the video, but it keeps all the objects intact, which I think is actually an amazing effect. But it's possible to this region detection capability. And you can do a lot of things with that, like isolate more moving things and more objects more easily, and therefore do some understanding on that data. This is an example of synaptic segmentation, actually. And what synaptic segmentation does, it pretty much colors each of these objects in a particular fashion, right? And that color helps also isolate the object from the environment. And it gives some sort of percentage characterization to each of name, label name and percentage of likelihood of that object being labeled that to each object. So it's also another thing that can help with video understanding. And then if we take a key point model like key point RCNN, we can then get the key points of people as they're moving through, and therefore, like if we're trying to detect if there's a person, the key point detector will clearly do that. And for example, our automated driving system or some other system will know to, be careful because there's a person detected. So those are some just advanced techniques. I don't have the code for them here, but I've written the code for them, and they work pretty well. And I'll share it at some point. And so let's talk about loss functions in video understanding. So loss functions, as you know, in standard neural networks have there's this idea associated with them that you need to essentially minimize the loss objective through gradient descent in order to get close to the desired classification output. So it turns out that there's loss functions that are generally better suited to different videos, right? So the video on this, the slow video on the top is going to benefit from, if you're trying to do understanding on it, from using what's called a temporal consistency loss. And the temporal consistency loss in videos, it's very good for videos that have smooth transitions between scenes and perhaps not a lot going on, because you have a lot of temporal consistency. So you try to essentially minimize the temporal consistency loss in order to determine what's happening in the video. And again, it's much easier if there's not a ton happening, because it's pretty much more straightforward function to minimize the temporal consistency loss. This temporal consistency loss is a secondary objective function. We're still trying to minimize the mean square error, or whatever primary binary cross entropy primary loss metric we're trying to reduce, but through gradient descent and backpropagation. But we also, on top of that, have the secondary objective that we're also trying to minimize against. So you can think of the surface as actually being fairly complex, the loss surface that we're trying to traverse. But it can be done, as you can see, and as you've seen in the previous models. And temporal consistency loss struggles with abrupt scenes because, again, the temporal consistency is going to be, inconsistency is going to be very high. And therefore, the loss is going to, it's going to shoot all over the place, right? It's best suited for gradual sequences. That's what temporal consistency loss is. What can we do about videos like this that are fast-moving videos of sports highlight reels where people are playing basketball or people are doing football, and it's transitioning from scene to scene to sport to sport to sport. You actually need to do something more, and you have to have a different loss function. And so we have contrastive loss in this case. And if you're familiar with how models like clip work or other kinds of models, contrastive loss is a loss function which which essentially brings closer pairs of objects together in the embedding space and keeps pairs that are farther apart in the embedding space that are different farther apart. So it's easier to demonstrate the contrast in that space via this minimizing the contrastive loss. And so the pairs that are closest together, bringing them closest together, and the pairs that are farthest together, negative pairs essentially being much more distinguished in spacing. So it's easy to figure out via some similarity search where a particular new inference should go. And the contrastive loss is good at capturing the underlying semantics across frames using augmentations. And so that's important because the underlying semantics is really what we need to understand, like what's happening in the video is going to be easy to do especially if we do it across frames and scenes. For example, it would understand if the scenes are changing a lot, that one, in context, many actions are happening, and two, perhaps the semantic information of the overall context gives the potential fact that it knows that this is like a highlight reel or something like that. That's what, you can, given, a significant enough model, you can possibly train it to do very deep semantic analysis. And it does tolerate abrupt scene changes, which is why it's important, right? Because, it's sort of self-supervised in the sense that it's sort of bringing its closest training together, or semi-supervised, bringing its closest training together and splitting apart its farthest training. And it's really good for a large-scale unlabeled data sets, which is the type what we would like to have for video understanding, and that's why it's essentially a technique known as self-supervised learning. Okay, self-supervised, right? It kind of like, readjusts itself and through its own examples, and using this contrastive loss kind of like refines the embedding space so the understanding is made better. And so if we were talking about the embedding space, so we should talk about different kinds of embeddings, right? And in video understanding models, there's different kinds of embeddings. For example, there's frame level embedding. So at each frame, in isolation, we can capture understanding of what's going on in each frame. And so that, could be like similar to like straightforward image understanding. What's happening? There's a tennis player. He's holding up a racket. He's probably playing tennis. We don't know. It's just one frame. He could be posing or whatever. But overall, that frame has some isolated context. And we can do things like object tracking and object detection because we can determine where an object is in the frame at least, if not what the overall context of the video was happening in the frame. Then there's segment level embeddings. And what do segment level embeddings do? They aggregate features over short frame sequences, balancing temporal context and computational efficiency for event detection and temporal modeling. So again, segments, like if you can break a video down into several segments, you could be like, what's happening in this segment is that people are playing basketball. What's happening in this segment, playing football. What's happening in this segment, swimming. I mean, there's like, these segment embeddings are like good in a sense that they provide a certain amount of understanding of what's happening in the video, right? And they can also, be designed to predict what's happening in terms of the transition of one segment to another. And that's another advanced topic. But and then there's global level video embedding, which gives you the total scope of the entire video. And if you need to summarize what the video is about, this is probably the best way to go about it, because the first one gives you possibly people who are holding tennis rackets on their frame level embedding. Segment level embedding gives you playing tennis, playing basketball, swimming. Global level embedding gives you sports highlights reel, right? And so it's important. All these levels, granularities of embeddings are actually important for video understanding, because there's all these contexts are to consider, and there's different storage requirements for embeddings based on the cost associated with these contexts. And then there's the idea of hierarchical embeddings, where you can combine frame embeddings, segment embeddings, and global representations, so you could get more fine-grained embeddings and more nuanced embeddings in terms of context. Now, again, another topic to go into, but basically what you're saying is you're taking all the best of both worlds of all the previously differing resolution of embedding space in terms of time, and getting a more complex embedding space. And so here, complex but potentially efficient, right? We want a balance there. And so I have this video of playing tennis again, and basically the kind of creation or visualization of the embedding space in 2 dimensions, kind of as the video is moving around. And as you can see, it's hard to tell exactly what's happening, but I think it's just an interesting visualization, which I basically did on each frame by computing the embedding vectors for each frame. So, embedding storage, right? So embedding storage are high dimensional typically, and they require efficient storage solutions like vector quantization or dimensionality reduction. And so we need to essentially, this is why we were talking about embeddings in the previous frame, because video data is very highly dimensional, and we need to figure out some sort of optimization strategy in storing the intelligence and the weights. And that's what the embedding storage that we use should definitively help us in potentially storing this effectively, and also in a multimodal fashion, which this is all multimodal data, so we have to keep aware. Each video may consist of multiple embeddings, frame-wise or segment-wise, right? So you can, again, as I said, these hierarchical embeddings are an example, right? You can create some sort of tree of embeddings associated with a top-level embedding to get more nuanced information of what's going on in a more efficient way. Video data sets can produce billions of embeddings requiring scalable distributed storage architectures, right? So this is important because just again, the amount of embeddings can be untenable, and we have to do something like dimensionality reduction to get rid of these embeddings, but we have to get rid of the right ones, otherwise the understanding part becomes distorted. And then now combining the ML part, which are the embeddings, with associated metadata like standard meta tags can actually provide much more intelligence. Like the most fancy thing to do is really not use any meta and be able to understand what's happening in the video. But sometimes, you're going to have situations where the context is very difficult to determine, even given your training, and you can simplify that a ton by if someone is labeled or something has like already produced meta, where you could have you can kind of like offset some of the understanding to that fact that meta, that timestamps, that labels were produced priorly. But this is important. This is different. This is actually a much more advanced topic because in this case you require designing your vector data store in a very particular way, and you also have to design your schema of storage of meta to combine properly with your vector data store, because you can do, you don't need your vector data store could potentially be some sort of structured data table like a SQL table, but whatever the case is, it's going to be much more involved. So let's talk about multimodal models, audio, video, and text. Okay. Multimodal models, there's many examples of multimodal models out there. This model on the right is an example of the Merlot model, and I'll go into that in a bit. But basically, a multimodal model takes both language and video, right, as separate things, and tries to combine them to do video understanding. And so when I go into the Merlot model in a little bit, you'll see why this is important. But this example of the model uses a joint vision and language transformer encoder, right, to determine what's happening in the video. And there's also mass machine learning in here as well. And there's temporal ordering as well to make sure that there's ordering of sequence tasks. But you can see that there's a word embedding along with a feature encoder, and that's going to help understanding what's happening, as well as the mass learning component that goes into this joint vision and language transformer encoder. And I've left out the details of this model because it would be overly overwhelming. So the Merlot model. So Merlot learns from video frames, audio and text transcriptions, and subtitles in a time-aligned manner to understand the context and relationships between modalities. It's actually a fascinating model because this particular model takes a bunch of YouTube video. I think it's like 6 million YouTube videos or whatever, and it takes videos of these actions and takes the transcripts to create sort of like learning a masked language inference on what's going on. So this is super interesting. Let me try to explain. The Merlot model, firstly, what it does is captures event sequences and the progression of those event sequences over time. So basically what's happening in this video, it can kind of give understanding the context, and it can actually infer potentially what's going to happen next. So this model not only determines what's happening, but also is a prediction model for what could be happening in the future, which is a very important and interesting example of. It employs a transformer-based model to integrate and change multimodal inputs and align multimodal inputs. Okay, so remember, one of the things is that with difficulties, and if I've talked about multimodal fusion before, one of the difficulties of union modalities that are combined is that the information is misaligned with the context of the video. And so something that's said to be happening at a particular point may not be happening there. That would confuse the model. So you essentially need an alignment process in a cross-modal manner to bring these the two unified vector stores together. And this kind of model here is awesome because it's designed for tasks like question answering, native understanding, action recognition, multimodal summary, a bunch of tasks the Merlot model is capable of handling. So if you go to the site, you'll be able to see that there's this pull-down menu, and this pull-down menu looks at random images and kind of says what's happening in this image. And it's a cool site. It's family-friendly for the most part, and check it out because it employs the Merlot model in this very interesting way here. Now, how do you evaluate video understanding models? I'm only going to go into this briefly because evaluation of these models is actually fairly complicated, but you can actually check out the leaderboards on Papers with Code. And the leaderboards, the models that I showed you here are actually, powerful, but they're definitively not like the most powerful. They're like more general and entry-level models. So you can have more specific models that are trained on specific data sets. And there's a much more powerful model called OmniVec2, which will, I think, produce a whole lot of better video understanding should you be able to set it up to do so. But we can see that the percentage sort of increases over time, and over all the way up to January of 24, where was OmniVec2 came out. And so, if you were one of those people who watches leaderboards for model performance, there's a Kinetics 500 leaderboard, there's an AVA Kinetics leaderboard, and then there's a Charades leaderboard for different models that use those data sets in different particular ways. So for video for action recognition, for simple, straightforward action recognition, for multi-actor action recognition in the AVA set, and for interactions between people and more complex recognition in the third set. The interactions being important for the third set, and that's why you need the Charades data set to. And if you want to model what's happening on that, look at Papers with Code and look at the Charades AVA data set and the models that are performing really well. The Charades data set and the models that are performing well against it. And so here's like the action recognition on AVA 2.2, and as you can see, all the way up to July 2023, there's many other interesting models that have come out to benchmark themselves against this AVA data, and then the action recognition finally on Charades, which I was just talking about, and all these additional models. There's even a model called super events. There's just advancements. And finally, we get into data requirements and annotation and video understanding. So, how do we train what happens in a video? How do we collect the data? What do we need to make sure that's in the data to make sure that the model can understand what's happening? And so annotating video data is labor intensive due to the need for tracking actions across frames. So not just labeling static objects, right? But annotating video is challenging because you have to do this manually, or you have to employ some sort of process to do this. You have to hire people to annotate video. So you're not just putting a label on, oh, this is a pot or a pan or something in the video. You're like, what is this thing doing? You have to annotate that properly, or get that annotation of action from somewhere, because it's not going to be generated automatically. Though I could see a future where video captioning does take advantage of this type of model and does generate those captions. Large-scale data sets like Kinetics and AVA are required to train video models effectively. Large-scale data sets like Kinetics and AVA, you need, again, a lot of data to do this, right? Like Kinetics and AVA were trained on a large volume of clips, right? Thousands and thousands of clips. And that amounts to huge amounts of data, and so you're going to have to apply the training to any of those models, which the amount of weights will be exploding at that point. And then the video models rely on temporal annotations, meaning every frame sequence must be carefully labeled, which increase cost and time, because it's not just individual objects annotation, but this is also sequence annotation. So you can see already with these three, it's very complicated. And then self-supervised learning offers a promised solution by reducing dependency on large labeled data sets. So if something is self-supervised, then a part of the annotation task goes away. You no longer need to deal with it. As we said, that some models use contrastive loss, and contrastive loss is a loss function which is part of a self-supervised system where the model is sort of understanding some of this intelligence on its own by modifying the embedding space, or modifying the calculation that's made to test against the embedding space. And so, if you've seen the MetaConnect video, which I believe everybody has at this point, you've seen
this is the new MetaQuest 3S.
So I'm not going to go into the video there, but you know that a lot of interesting things were introduced because of MetaConnect, and if you want to watch what's happening in this video, I'm fairly certain that video understanding is taking place in the models that are behind the technology unveiled here, to some degree. So thank you very much. Appreciate it. That was a long presentation. And here's some papers. And yes, I'll see you next time.